Um, so let's get started. So welcome everyone. Thanks for joining on Zoom if you're here on Zoom. And if you're watching this on YouTube later, so hopefully you're home so safe. I'd move it on. So the entire lecture on Zoom or online. It's not snowing outside here yet, but apparently it's supposed to be snowing a lot, about 2 inches an hour with strong winds by the end of the lecture. So I thought it'd just be better to put everything online. So it's also, so easier for the people online and for the instructor if it's entirely online instead of hybrid. So the good thing is I'm lecturing, but I've also got the chat open. So if you have a question, you want to add something, add a comment, I can much more easily monitor the chat as well. If you have a question, you want to kind of raise your hand, you can do that. In that, I will call on you as well. So if I'm doing this at home, I can do all this at the same time. So the other fun thing about doing it online is that I can pipe in some background sound. So in case I do something really cool, I can make it so everyone applauds. Or if I don't do something good, I can have it so everyone boos as well. So yeah. So okay, that was a little bit longer than I thought it was going to be, that sound. All right. So please feel free to jump in with questions or comments if you have them. So today we're going to be talking about expectation, and this is an important property of distributions, and will play an even larger role in the statistics section as well, although that expectation will be slightly different than what we'll talk about today. Yeah, so let's just quickly look at the schedule. Notably, homework 3 is due today. We had a bunch of off-stars the last couple of days. Hopefully homework 3 is going well. We've seen a lot of people upload this to Gradescope already. I will be available for about an hour afterwards online here to answer any questions you have as part of my office hours. So if you have more questions about homework 3, I can answer those after class here. So there were a couple of questions or things I'll just remind people about. In particular, homework 3 has some parts where we ask you to do stuff in R, right? So here what is this one? This is 3B. You're asked to to plot your answer. And so what we would like you to do is to generate the plot in R, and then kind of if you're doing this on paper and you finished everything else, scan that, and then or if you have the PDF, then insert the picture from R in here. It's not too hard to do with like Adobe, or with like Apple Preview. Hopefully you can do that before you upload. If you upload that as a separate page, it won't be recognized by Gradescope. So just kind of just a reminder about that. So great. Also I'll say the grades on the quizzes have been, we should have hopefully the grades out for homework 2 maybe by the end of the day. There was a few delays on those, but so hopefully that'll be out by the end of the day. And the grades on the quizzes have gotten a little bit lower than I was hoping for as a class. I know, so there's some parts of that where I think we will hopefully get better at that through the way I use the lecture time. So I'm going to make a few small changes and see if that helps. But so keep making sure you're kind of, if you have questions about the material during the week, make sure you ask questions and we can try and clarify that as well as you're going. Okay, so let's get into the lecture. Again, feel free to put stuff in the chat or to raise your hand during the lecture. I can call on you to speak as well. So expectation is like a really important concept, and so its definition is going to be slightly different for discrete random variables and continuous random variables. As you'll see, they're basically, one is like a generalization of the other one. So we'll start with discrete random variables. That's a little bit easier to understand the underlying mathematical formulas. I think for continuous random variables, there's actually a more intuitive way to think about it. But we'll start with the expectation for discrete random variables. Okay. Expectation for discrete random variables. All right, so we're going to think of having a random variable, so x, okay, and it's going to have a probability density function, sometimes called a probability mass function, so f, that's going to have some domain. So we're gonna call these values AI, right? For some value I equals 1 up to say so n, and remember this maps to some real values. Okay, then the expectation is a property of this random variable. So x is drawn from this PDF f, and the expectation, I will like to write this as an uppercase E and then square brackets. So around the random variable. So this would be the expectation of x. Okay, there's a lot of different notation. And so around how this is used, this is probably the most standard one. I think this is the most clear way of doing it, but it's often an uppercase E, if you think of as a property of the random variable. Okay, and this is just the sum. Let me make sure I write this clear. This is a sum over all values, so I, that the random variable can take. Let's say from 1 to n, there are n possible values it can take. Okay, and I take this, this random value, and I multiply this value that the random variable can take times the probability that x, the random variable, takes on this value. Okay. This is equal, I equals 1 to n. This is just another way of writing it with the probability, density function, f of, AI. That's because for a discrete, random variable, we have that f of a is equal to the probability that x is equal to a. Right? So that's true for a discrete random variable. So then we can write it down as, this formula, okay? So the way to think of it is if I look at all the values that the random variable can take, and I multiply each of those times the probability it will take that value, and I add all those up. All right, so this is kind of like the average event that can happen, right? So if I were to look at all the possible outcomes of this random process, When we're talking about random variables, these are going to be things that take on a real value, right? So and I somehow want to take the average of those things. So the averages of these AIs, and that's weighted by the probability. Okay, so it's a weighted average, right? So I can think of so let me say it's the so I can think of this in words as the average value that the random variable x takes. All right, so it can take on a bunch of random variables. This is the average one. So another way I'd like to think about this is that these weights or these probabilities have the property. I can think of them as weights. Okay, so let's say this is this is a weight associated with this value AI. Okay, I have the property because these are probabilities. I can think of these weights. I know that this is in 0, 1 because it's a probability, and I know that the sum I to n of the weights is equal to 1. Okay, so what that makes, I can then think of the expected value of x as the weighted average I equals 1 times n wi times ai. Okay, so again, this is just the same formula as before, but now I can think of this as a weighted average. So if all of these weights were the same, they were all the events were equally likely, then this is exactly the average of all the possible outcomes. Okay, but if they're not equally likely, well, then that average takes on more weight if there's more probability of that event. Right. So let me we'll go through an example a bit later if we think about like the average of like a die, but if it's like and we roll the die, if we have a weighted die, then you kind of change this. So then you change this formula a little bit. And so it's sometimes nice to think of this as a weighted average as well, right? But if each of the if each wi is 1 over n, right, then the expected value is 1 over n sum I equals 1 to n of of AI. What's happened here is that I've taken this wi, and if this is equal to all 1 over n, then I can bring this factors out in from the sum, right? So I've moved it out on the left side. Okay, so you can think of it as a generalization of just an average, but I'm changing the weights of things. Okay, they still have to add up to 1, and they still have to be between 0 and 1. So okay, so let's do some examples of this. Okay, so let's see. So a simple example. Okay, a simple example is if x is from a Bernoulli random value from a Bernoulli distribution, right? And so who remembers what a Bernoulli distribution is, right? What values can the Bernoulli distribution take? This is one of the ones we talked about in class so far. This is a discrete random variable. Describes a discrete random variable. What values can a Bernoulli random variable take? You can put in the chat. And now, so 0, 1, 2 is close. Yeah. So 0 or 1, right? So a Bernoulli random variable can be, X can either be, is an element, X can be from 0 or, so 1, it's like a binary, so random, so variable. Okay, and we say that the probability that X is equal to 1 is equal to P, and the probability that X is equal to 0 is equal to, so 1 minus P, right? These are the only probabilities. These two things have to add up to 1, right? The P and the minus P so cancel each other, right? And so there can't be any other events. Or I can write this as, so the PDF, of X equals P if X equals 1, 1 minus P if X equals 0, and 0, so for everything else, right? So this is a Bernoulli random variable. It's the probability of flipping a coins. If you flip a coin and it lands on heads, if it's not necessarily a fair coin, but if it lands on heads 2/3 of the time, then this describes that random variable with P equals to 2/3. This is a Bernoulli random variable. In this case, what is the expectation? What is the expectation of X here? Okay, I can write that. So maybe 0.5. Yeah, so it could be 0.5, but it's going to depend on the parameter P, right? So if it's a fair coin, that's gonna be the right thing, right? If it's 50% 1, 50% 0, then the answer is going to be 0.5. But it has to depend on this parameter. So as you're thinking about that, let's write out the equation for expectation. Remember, I can either be 0 or is either 0 or 1. Okay, and so it's going to be this value I times the probability that X is equal to I. Right? So if I expand this out, that's going to be takes on 0 times the probability that X is equal to, let's just do this slowly and clearly, the probability X is equal to 0 plus 1 times the probability that X is equal to 1, right? And that is equal to 0 times 1 minus P plus 1 times P, right? And we can see that anything multiplied by 0 is, 0, so this term goes away. 1 times anything is doesn't do anything. So we're left with just the answer P, which is what, so someone put in the chat. So great, yeah. So it depends on the parameter P. It always depends on the parameter. Sometimes expectation, that parameter is given because that parameter defines the expectation. And that's the case here. Actually, so it said it depended on the parameter P, and that's actually the answer for the expectation. That's not necessarily a coincidence. This is a kind of a common thing with these distributions. All right, so if you have a fair coin, and you get 1 point if it's a heads or 0 point if it's a tails, then the expected number of points you get is going to be 0.5. If it lands on the heads 2/3 of the time, then and you get 1 point for heads and 0 point for tails, then the expected number of points is going to be 2/3, which is the same value as P. Right, so okay, great. So this is a pretty simple example. Let's do a little bit more complicated example here. Okay, let's look at a a geometric random variable. Okay, X is now a geometric random variable, again with a parameter P. So the expectation is going to depend on this parameter P. All right. So what is the probability, right? So, okay, so who remembers now what values can the random variable X take on, right? So what is a geometric random variable represent? So if you remember, you can just throw in the chat, what values can X take on? So X is going to be in the set of, so what? Remember what the geometric random variable represents? So it's nothing to do with actual geometry, which is very kind of disappointing with me, but has to do with kind of like a geometric decay. So real integers, yeah. So it's so close. So real, yeah. So right. So it's not going to be it's not going to be all the real numbers. It's not going to be any so imaginary numbers, but it's just going to be all the integers. That are not negative. Okay, so it's going to be 0, 1, 2, up to so and so on. So it's going to be all non-negative, so integers. All right, and if remember, if you look at the PDF for a random variable at the value, so I, this is going to be kind of, so what this is saying is that I have some probability of an event occurring, like, flipping a coins, that's heads, and I want to know the number of times I need to flip it until I get the first heads, right? So that's what the geometric random variable is. Okay, and so I can write this down as the probability that I get I, that means like if it's like I need 7 flips before I get the first head, right? Or this was the homework question about the toaster. How many times do I put a piece of toast in the toaster until till the toaster catches on fire? So I'm going to have 1 minus P, meaning the probability it did not catch on fire the first several times, I minus 1, times P. On the ith time, it did finally catch on fire. Okay, so the first I minus, say, 6 times, it did not catch on fire. And so the probability that happened in each time was 1 minus P, because it catches on fire with probability P, and then with the P time, it does catch on fire, right? So this is a geometric random variable. Okay, and we want to figure out the expectation of X. Okay, I'm going to write down the formula for this, but I want you to think about intuitively what might the answer be as I'm writing this down. Okay, I equals 0. Yeah, actually, sorry, this cannot take on 0. Yeah, so I equals 1 up to infinity. Okay, it can't. Infinity is an actual number, but this saying it could be an arbitrarily big number. So it might take 1,000,000 times before the toaster catches on fire. But turns out that's going to be very unlikely, and so I can still calculate this sum. Okay, and so this is going to be, and remember the sum is going to be this value I times f of x of I. Okay, and this is I equals to 1 times infinity, I times 1 minus p to the I minus 1 times p. Okay, so this is the expectation. This looks pretty intimidating if you're not used to like these infinite sums. So let's start by thinking of a kind of a simple example of what this would be. What if the probability was 1/2, right? So what if so let's start with example. Let's say p equals to 1/2, and let's start so writing out this sum. Okay. Okay. So the terms in the sum is going to be so the expectation of x is going to be 1 times the probability it happened on the first term, right? So I minus 1 is 0. So that 1 minus p to the power 0 is just a 1. So I ignore that times p, right? So this was, and p was 1/2. Okay, so that was pretty easy. That's the first term. The second term is times the probability it happens twice, right? 2 times the probability it happens twice. So this is I equals 2. Now the probability it happens twice is 1 minus p, which is also 1/2. So we have that 1 minus p is also equal to 1/2 in this case. So this is a nice case, right? So 1 minus p is also 1/2. So I have 1/2 times 1/2. Okay, this is actually plus 2 times 1/2 squared. It'll be useful to write that. Okay, now let's look at the third term. The third term is now going to be that 1 minus p happens twice. That's 3 minus 1. So I'm going to have 1 minus 2 to the power 2 times 1 minus 2. And this is actually 3 times 1/2 to the power 3. Yeah, so okay. So this is and then I'm going to keep getting more terms. So more and more of these terms. So okay, so I'm going to have an infinite number of terms, but the sum is not going to go to infinity. I'm not going to, if I add all the terms up, it's not going to go to infinity, because what's happening is that this part of the sum, the probability is decaying, so geometrically. That's what it's called. When you have a fixed value and you, I guess is decaying exponentially with the sum. So this is something that's called like a geometric decay. That's where the name comes from. So that term is going down, right? So maybe you've seen before that if I have I equals 1, so the sum from I equals 1 to infinity, and I take 1/2 to the power I, this sum is going to be 1/2 plus 1/4 plus 1/8 plus 1, so 16th, ... And this is gonna, in the limit, this is gonna be exactly 1, right? I keep getting halfway to the goal, but I'm never gonna get past 1. So I'm kind of seeing that here, but I also have kind of these other terms here in front, this 1, this 2, this 3. So it's not gonna be just 1, it's gonna depend on those other terms. So I've got this part that's increasing and the part that is kind of decaying exponentially, and the exponential decay is going to win, right? That is dropping faster than the numbers are increasing. Okay. All right. Okay, so this gives a little intuition why it's bounded. Okay, so who's thought about this now? What is this answer? Who thinks they have a good guess? At least for the case with the random, with the even coin, how many flips should I expect to do until I get a heads, right? So that's what this p equals 2, p equals 1/2 case is. And so I can write it out as this infinite sum. So I'm going to have, with probably one half, it comes the first time. Probability 1/4, it comes on the second time. Probability 1/8, it comes on the third time. But in expectation, how many so do I expect? So guesses? So if you flip a coin, a fair coin, how many times should you expect until you get a heads? You think about 10 times, does that seem about right? You expect to flip it about 10 times before you get a head? No, you can give me some thumbs up or thumbs down on there. So one time you expect, yeah, I think one, yeah, so somewhere in the range of like, so one or two, right? If you flip an expectation, but I don't, half the time I don't get it on the first flip. So it should probably take more than one flip. And so it turns out the answer here is, so in this case, it's going to be 2, right? So the expectation here, the expectation of X with a fair coin is going to be equal to 2. If you flip a fair coin, you expect on average, after 2 flips, about half of them are going to be heads. So on 2 of them, you expect to get a heads after 2 flips. Okay. So now let's say we're changing this so that it's not a fair coin. So let's say instead we're rolling a die, okay, and we want to know how many rolls until we expect to get a 4, right? So if we now say if we have a die and it's 1/6, the expectation, the probability of getting a 4 is going to be 1/6 because I have 6 possible faces. So 1/6 the time I'm going to get a 4. About how many do you think it'll be more rolls, more than 2 rolls to get a 4, or less than 2 rolls? Yeah, right. So great. So it should be more rolls because it's less likely, right? So the smaller P is, I should get a larger number of rolls. And so does anyone have a guess on how many rolls I should expect? Yeah. So 6. That's the right answer, right? So for a die, so if X is a geometric random variable with P equals 1/6, then the expectation of X, the expect number of rolls to get a 4 is going to be exactly 6, right? And so someone in the chat has guessed that the expectation of a geometric random variable in general is going to be 1/P. It's going to depend on this parameter P, right? So as P gets smaller, the expectation gets larger, right? Great. Okay, so another question in the chat is, okay, is the expectation always going to be an integer? All right, so let's see, will it always be an integer if it's 1/P? Can you imagine a situation where it's not going to be an integer? So far, we've had a 2, a 6. It's a discrete random variable, so that seems like maybe it has to be an integer. But let's say that it was a non-fair coin, and the probability of getting a heads with something like 2/3, right? So if P is equal to 2/3, then 1/P is going to be 3/2, right? So if I'm more likely, so for instance, if we have a die, and I want to know the probability I got a value greater than 2, right? 3, 4, 5, or 6, right? Well, then the probability is 2/3. I'm going to get that, and the expected number is 1.5 rolls before I get something larger than 2, right? So it does not have to be an integer, right? So this is a little weird. The expectation, this was true with the Bernoulli random variable as well. But the expectation does not have to be something that was one of the possible outcomes of the random variable. It can still be, it can be a real value, even if the outcome is discrete. All right, so that can be a little bit, it can be a little bit tricky to think about. So, okay, great. Okay, so I'm thinking of giving you a question. So let's say I have a die, and on a roll, I'm going to get, so X is going to take on the values I with, so it's with probability, let's say, we write this. All right, so it's I'm going to have a random variable, which is going to be a like a fair die, and so f of x is going to be for 1, 2, 3, 4, 5, or 6. Gosh, okay. So with probability 1/6 for, okay. So the probability is going to be 1/6 for x equals 1, 2, 3, 4, 5, 6, and it's going to be like 0 otherwise. What is the expectation of x? Okay, I would like each of you to work this out. So how about I'm going to give you a minute to work it out. So it's roughly a minute, and then I'll tell you to all put the answer in the chat. Okay, so write the expectation of the value you get from a die. All right, so if the question is not clear, feel free to ask, but otherwise, in a minute, I'll ask you to all put it in the chat at the same time. So hold off on doing that for now. So, okay, so is everyone done calculating? If you need a little bit more time, let me know, but all right. I'm going to count from 3 down to 1, and you can all put the answer in the chat. 3, 2, 1. Okay, post. See if this works. All right. Yeah, so it looks like almost most people got their answer. A few people got 6, which is, so it's probably easy to make that mistake, but most people got 3.5, which is great, right? So let me just write this up pretty quickly, right? So I can just consider I equals 1 up to 6. I do I times the probability equals 1/6 for each of these, right? So this is, this value is the probability x equals to I, right? So now I can factor out the 1/6. Sum equals I equals 1 up to 6 of I, and this equals 1/6 times, so 21 is the sum, right? And so someone wrote up 21 over 6, and that's exactly right. And so 3.5, right? So, okay, great. So figure out how to do that. I mentioned earlier, this is an example where all the probabilities are the same, right? All these probabilities are the same. And we could think of these as like a weight, and it's actually an average over all the values. But if instead we wanted to say it was not a fair die, and we wanted to put more weight on, so one of them, say it was one of these trick dies, and half the time it's going to be 1, and then it's equally likely among the rest. Well, we're just changing that weight, and we're taking a weighted average. Okay, so something that's useful to do if you're doing the expectation of x, and x is in some, and we know x is in 0, or is in, so some range from 1 up to, say, 6. But it's really, this is a subset of 1 to 6. I know it's between 1 and 6. Okay, if I do a weighted average of these things, it means I don't even know what the probabilities are, but I know that the expectation has to be less than 6 and has to be greater or equal than 1. Okay, so that's kind of a good thing to check. So 6 showed up in the calculations, but it's so it's not outside this range, at least, right? If you got 21, and that's outside of 1 and 6. If you just added them up and forgot to divide by 6, that could be a common mistake. It wouldn't make sense because the expected value have to be somewhere in the range, but it doesn't need to be one of the values. It doesn't need to be an integer in this case. It could be some kind of continuous value like 3.5. All right. So, okay, great. So those are expectations on discrete random variables. Those are kind of the main things to kind of think about here. Let me jump to on continuous random variables. There's slightly different, but it's just going to be a generalization. Expectation on so continuous random variables. Okay, and so if remember, we have x, and it's drawn from some probability density function f. Okay, and so then we can define the expectation as equal. Now we can't take a sum because it's not a discrete set, but x could take on some real value, right? So x takes on values in the reals from negative infinity to infinity. So we're going to have an integral instead. So let's say takes on values x equals to negative infinity to infinity, and so some integral of the value x takes times its the density of this value, right? Which again is not a probability, but kind of is representative of the probability. Okay. Okay. So this is the definition now for a continuous random variable. Okay. This looks more complicated. Instead of a sum, that I'm summing over all the elements and multiplying them by the probability and adding them up. I'm kind of doing that, except I can't add things, so I have to do so I've got to do like an integral instead. Okay, so if the way I like to think about this is if we have some x's in the real values, right, from negative infinity to an infinity, right? These, it eventually reaches these. We can think of f as this function that we can evaluate, right? So everywhere, right? And this kind of describes kind of the area under this curve corresponds with the probability. Okay. If we draw a picture like this, what we want to do is realize where the expected value is going to be. This might be, if this is f of x, then this might be the expected value of x. Okay. And so I like writing it like this, so this arrow, because the expectation is exactly where, if you were to put your finger underneath this sort of distribution, you're to put your finger right here, and that the green area corresponded as a weight, then it would perfectly balance on your finger. Whereas if I were to put it over here instead, and I would put my finger there, it's gonna tip over. Okay, so the expectation is kind of this balancing point. Okay, it's not necessarily that there's the same amount of mass on either side, because I could also get a picture that looks like this, where I've got a big bump over here, and then a small bump here. Okay, so if I get a picture like this, I've got to have a little bit of mass there, but it's far out, and then a lot of mass here. Okay, the expectation is going to be somewhere here, maybe a little bit here. Now, this is not saying I've got the same amount of mass on either side, but the mass that's out by the edge here, because it's further out, it pulls down more, right? So if you're working as like a waiter or waitress, and so if you're carrying like a tray of stuff, see if I have a prop. Okay, if I'm carrying a tray with stuff on it, right? I want my hand to be under the mean of all the weight. If my hand is not under the mean, it's going to fall over. But I just need my hand to cover this mean. And if I put something, okay, but even if I have it in the middle, but I put something very heavy on one side, that means I have more probability right here. It's gonna fall over. All right. So this mean is this balancing point of this sort of distribution. Okay, and so it's kind of a useful way to think about this. So you can write it mathematically as this integral. And okay, so what if you might be thinking again, well, I'm doing this integral over negative infinity up to infinity, right? I have to do this, evaluate it at these infinite, integrate an infinite span of things, so like, how is this going to be possible? Well, we had infinite sums already with the discrete random variables, and we could still calculate the expectation. And we know that if I integrate just this term, just the f term over this infinite from negative infinity to infinity, that integral is 1. So I know it shouldn't be too big. It shouldn't be too bad. I have to worry about if there's a lot of mass as x gets extremely large, then something bad could happen, okay? But in general, for a lot of random variables, this expectation is still well-defined. Okay, and so the ones we'll talk about in this class, the expectation is going to be well-defined. You sometimes deal with some properties where this expectation with this infinite integral is not so finite, then those are kind of messier things, right? Beyond the scope of this class, at least. All right, so okay, let's start. So kind of start with an example here. Okay, so let's say that I have x is a continuous random variable from the exponential distribution. Okay, the exponential distribution, this is like the continuous form of the geometric distribution. So things are decaying at a rate, but they could occur at any time. So if you think of the thing of the time from now until when I expect it's going to start snowing, right? I kept expecting it was going to start snowing at this point. It hasn't started snowing yet. So my house, but at some point in time, it's going to start, snowing. And if I'm measuring the unit in minutes, lambda is the probability it starts snowing so that minute. Okay, and if I make that interval that I'm measuring to seconds and keep getting infinitely smaller, but keeping this rate constant for the minute, you can kind of reduce this to the geometric random variable. So okay, maybe if we have maybe at some point I'll do that derivation. It's in the notes, but so what we need is the PDF of the geometric random variable. And if you remember, the PDF of this, let's just say f of x is going to be equal to lambda times e to the power negative lambda x. Okay, so this is the PDF for x so greater or equal than 0. So that's all right. So this is PDF of this, and it's 0. So otherwise, okay. And so if we write out the expectation of x for this random variable, then I only need to integrate. Remember, I need to integrate from negative infinity up to infinity. So we'll write this for x, f of x, so dx, okay? But I can change this to 0 because since f of x equals 0 for x so less than 0. So I can start the integral at 0, right? So this makes it a little bit easier. So I can do the integral for x equals to 0 up to infinity. For x times lambda e to the negative lambda x, so dx. Okay, and you could calculate this. It's going to act similar to the geometric random variable, and the expectation is going to be 1 over lambda. Okay, so lambda is kind of the expectation, is kind of the rate per kind of the units I'm measuring in. So the kind of the probability roughly it happens per minute, right? And so, but it can happen at any point of time. And so, so it's kind of like the geometric random variable where lambda is equal to p. Okay, and so then the expectation is 1 over lambda. Okay, and I don't know, I think it's worth to drive all this, but just as this is a known expectation that you can look this up on Wikipedia in these notes in the book, right? But the expectation of this random variable is 1 over lambda. So, okay, so for an exponential random variable, let's do one that I think you should be able to figure out on your own. Okay, let's say that we have x is from a normal distribution. We'll just say n mu sigma squared. Okay, so the normal distribution, remember what the normal distribution is. F of x is going to be equal to 1 over sigma square root 2 pi. Okay, this is kind of a constant here, times e xp minus x minus mu squared over 2 sigma squared. Okay, so this is the definition of the normal distribution. I don't have to condition on it being greater than 0 or anything like this. And I'm going to argue that the expectation of this one should be easy to figure out. So you can put a guess in the chat if you'd like. Let me draw a picture of it again, and hopefully this will help. The picture of this distribution is going to be look kind of like this, kind of like a bump, and then kind of decaying in both directions here. Remember, and I can kind of put mu here is this, so a parameter. X is going in this direction, it's real numbers, but that's increasing x, this is decreasing x. And we have this parameter sigma, which is roughly about halfway up about the, the width of this, okay? And so this mu is kind of the center of it, and we're measuring the distance, x minus mu, and I'm squaring that, okay? So I'm looking at, for some particular value x, right? I measure this distance, I'm gonna square that distance, so that means that x, or if I have minus x, right? So this would be kind of in the other direction. This would be, this point would be mu minus x minus mu. Yeah, so this is the difference vector, and I'm subtracting that from mu instead. Okay, so so if I do this value, let's call this x prime. X prime is the same distance from mu. So if I do x minus mu squared, I'm going to argue that this is equal to x minus mu squared. Okay, I just need to show that the distance is the same, because the sign doesn't matter. That gets made positive inside the square. Okay, so this is mu minus x minus mu minus mu. Okay, so that's what's going to happen is this mu and this mu are going to cancel. What's going to be left is minus x minus mu. And when I square that, that's going to be x minus mu squared, because the minus in there kind of, it doesn't matter when you square it. Okay, so what's important about this distribution is that it's going to be so symmetric around this middle point mu. Mu is the parameter, it describes the middle, and it's going to be so symmetric around some mu. Okay, this term, this looks very complicated. This term is just a scaling coefficient to make sure that it integrates to 1, right? So this is just a scaling, so coefficient, right? So it integrates to 1. And so, and then this term is just to kind of determine the scale. Okay, so but the point is it's going to be so this is going to be so like symmetric around some u. Okay, so if anyone can put in the chat who has a guess for what the expected value of x is going to be. Yeah, so it's just going to be mu, right? It's going to depend on, it's going to depend on these parameters, and it does not depend on sigma. It only depends on mu. It's because it's symmetric. That's going to be the balancing point of the distribution, right? Because it's going to have equal mass on either side. If it was kind of the skewed distribution, you have to be kind of careful, and like the exponential distribution is skewed in this weird way, but it's still, so to do the balancing point, you have to actually do the integral. But with the normal distribution, it's exactly that parameter. That parameter is chosen to tell you what is the mean of the distribution, right? So so you just kind of read off the distribution from the parameter here. So, okay. So great. Okay, this is another kind of important example, the normal distribution. This, again, you should be, this equation should, it looks kind of intimidating, but once you kind of start to see the parts of it, hopefully kind of it starts to look so normal to you. So this is a good equation to kind of look at it and try and kind of remember what this equation means and remember what the different, what those different parameters are doing. So, okay. Okay, so there's one more really important thing we need to cover this lecture, okay? And that is called the linearity of expectation. Expectation, okay? The linearity of expectation. And what this is saying is that expectation is this, is a linear operator, and that kind of means you can factor stuff out of it, okay? You can factor things out of these linear operators the same way that when we took a sum and we everything had the weight 1/6 when we calculate the probability, the expected value of the roll of a die. Everything had a probability of 1/6, so I can factor that out of the sum. Well, I can do a very similar thing with the expectation operator, okay? So I can write a random variable. So let's say I've got two, random, variables, x and y, okay? And so now I've got, I'm going to create a new, random variable called z, okay? This is z, my new random variable, and this is just going to be written as 2x plus 3y. Okay, so as I mentioned earlier, random variables are kind of, mathematically, they're kind of this tricky concept, but the power of them is we can treat them like variables in algebra or in like a computer program. And this example where I can take a random variable, I can add it with something, I can multiply it with something, and that creates a new random variable. And this is all legal to do, and this is kind of the point of having these random variables. Okay, so I have this new random variable z, and let's say I'm, so given the random variable x, its expected value, let's say this is, like the roll of a die, and the expectation of y is going to be like if I flip, the expected number of flips to get before I get a heads and a fair coin, it's going to have an expectation of 2. Okay, so let's say I get these, and then I get some points based on based on the combination of these things. And so now I want to calculate the expected value of z. Okay, so I can write this as the expected value of 2x plus 3y. And so now the linearity means I can factor out the coefficients and things across, sums. So I can write this as 2 times the expected value of x plus 3 times the expected value of y. I can factor out constant coefficients, and I can break stuff up by the sum. Okay, so there are two properties. You can factor out constant multiples, and so I can decompose so sums, okay? So if I have this first one is that expectation of alpha x is equal to alpha times the expectation of x. And this one is the expectation of x plus y is equal to the expectation of x plus the expectation of y. Okay? So if I know in this example here, now if I know this information, expected value of x is 3.5, expected value of y is 2, now I can solve this question. 2 times 3.5, I get, $2 for based on the roll of the die, plus I get $3 based on the number of flips before I get heads, right? And so I can put these together as 7 plus 6 equals 13 as the expected amount of money I would get in this this game I made up. Okay, the ability to to calculate stuff, this really can simplify a lot of calculations when you're trying to compute the expectation of something complicated. But you can write down that complicated thing as a set of simple random variables, and then I can get the the total expectation. So just by doing this, by decomposing it into simple pieces that I know the answer for. All right, so let me give an example. So let's say I roll 10 fair die, okay, and I add up results. So this gives me a random variable, s, right? So I'm going to have 10 die x1, x2 up to x10, and s is going to be the sum of their rolls, right? I equals 1 up to 10 of xi. Okay, so what is the expected value of s? Okay, so this should be, I can write this as the expected value of x1 plus x2 up to plus x10, right? Which is going to be equal to the expected value of x1 plus the expected value of x2 plus ... plus the expected value of x10, right? And we know each of these, the expected value of xi, we calculated that earlier, or you calculated that earlier. That was 3.5, right? So I'm gonna get 10 times the expected value. They're all the same of each xi, which is 10 times 3.5, which is 35. Okay, so I quickly wanted to do the expected value of the sum of the amount I get from rolling 10 die. I just do 10 times 3.5, 35, right? So it makes it very easy to to calculate this. Whereas if I had to work out the entire sample space, right, and say, what's the probability I rolled a 2 on the first one and a 3 on the second one and a 6 on the second one, right, and then work that all out, that would be a big mess, right? This really makes this calculation much easier than it would have been before, right? So you can maybe imagine trying to calculate this without knowing this trick. It would be a a giant slog. You could do it, but you would probably make a mistake somewhere along in the calculation, right? Where this way it's very easy, pretty simple to do. Yeah. So okay. So let's say I have a Bernoulli random variable, right? So let's do another example. this one you're going to solve. So now I say X is a Bernoulli random variable, NP, right? So this is a random variable where, if you remember, I have an event like a coin and I flip it n times, and with probability P, it's heads. Or with probability P, I get 1 point, probability 0, I get, or with probability 1 minus P, I get, 0 points. And I want to kind of take the sum of things, right? So this is the distribution of number of successes of n trials, each with probability P, right? So I flip a coin 10 times, or I roll let's say I want to count the number of 4s I rolled in a die. I rolled it 10 times, and each was probably 1/6, right? So that was probably the number of 4s, not the total value of all the die, right? So it's slightly different than the previous example. What is the expected value of X? Okay. So how would we approach this? The hint, it's going to use something. It's going to use the linearity of expectation. That's what we're talking about, and something we calculated earlier in the lecture. Okay, how would we use linearity of expectation, or how would we calculate the expected value of this random variable X? All right, so based off calculation, we don't have mu in this one. Yeah, so people are writing down n times p. Yeah, great. So how did you? Yeah, it needed to use the parameters n and p up here, and you're saying it uses both of them. So how did you get n times p? If you want, feel free to unmute and say something. Okay, expectation of a Bernoulli, great. So, right, so we have that if, yes, okay, thank you. First of all, I should have said a binomial random variable. I wrote up the thing for, Bernoulli. Okay, yeah, so the expectation for if we have let's say we have bi is a Bernoulli random variable with parameter p, expectation of bi is going to be p, right? So the expectation of a Bernoulli random variable is p, right? Okay, so and how's the binomial relate to a Bernoulli random variable? Right, it's the number of successes we had, where a Bernoulli random variable is 1 if we have a success and 0 if we don't have a success. So how does the binomial relate to the Bernoulli random variable? Yeah, so binomial is repeated Bernoulli, okay? So I could think of having n trials, and BI stands for the ith trial, okay? And I get 1 if it's successful, and 0 if it's not. So it says, let's say I ran just one trial, how many successful I got? That's exactly the Bernoulli random variable. And so I have that x, the binomial random variable with n trials, is going to be the sum over I equals 1 times n of the binomial of the n, so Bernoulli random variables, right? So the expectation, right? So that counts the number of successes. 1 if I get success, 0 if I don't. I can just count, add those up in order to get the count. And now the expectation of x is going to be the expectation of sum over I equals 1 to n of the, so Bernoulli random variables, which is I can factor out the sum I equals 1 to n of the expectation of the single Bernoulli random variable. This is equal to I equals 1 to n of p. And now I'm adding up n terms. Each of them has the value p. This is equal to n times p. Okay, great. So the expectation of x of a binomial random variable is going to be n times p. Okay, and I can get this from linear of expectation and the expectation of the Bernoulli random variable. So great. So okay. So these are kind of the core things we covered today. Let's kind of go back through these quickly just to wrap stuff up. The expectation of a discrete random variable, okay, is going to be in here. Expectation is kind of the average value it takes, and I can get that by summing up the value it takes times the probability it takes that value. And I sum this up over all the possible outcomes I can get. Okay. For a continuous random variable, I've replaced this sum over the things with an integral. And even though I don't have the probability of that it takes on a value x, I have this density function instead. And so I can use the density function as kind of like the thing in place of the probability. Because I'm integrating over all the values, this is going to be okay. So again, it's the integral of the value it takes x times the density of that value. And I integrate over that, and that gives me the expectation. And we wrote down a couple of examples. Right. So if we have, if x is from the, so if we have from Bernoulli with p, the expectation is going to be p. If it's from, so geometric with p, the expectation is 1 over p. If it's from binomial n p, the expectation is going to be n times p. These are all discrete. For continuous, if x is from the exponential with lambda, this models the geometric, and I get 1 over lambda. And if x is from the normal distribution with mu sigma squared, then the expectation is going to be exactly mu. Okay, and so these are kind of the properties of these distributions. And so you could mostly rederive those, hopefully, but kind of those are kind of things that sometimes I look up on Wikipedia for this or other distributions. So for the very simple ones, like the normal distribution or the Bernoulli, you should just be expected to know these and probably remember them or rederive them for the geometric or the binomial. And with the exponential, probably remember that it's the continuous analog of the geometric, and so the 1 over p becomes a 1 over lambda. But those are kind of the core things to remember in this lecture. So okay, great. So So we'll stop there. Let's see, I'm going to turn off the YouTube recording.